All right, so before we get going, does anybody have any questions about anything? Because that when I was grading the homework, the 9.7, I didn't cover that yet, so I want to cover that before we continue with the small signal models and stuff, okay? Unless you don't want me to cover that, then we'll continue on with small signal models. Yes? No? All right. Yeah. In the spice, yeah. Yeah. No, because remember our channel would be like this, right? When it's in triode, and then it's this. And if we want, we can put the VDS on there like that, right? There's going to be another, so this would be in the case when we're operating over here. So just as a sanity check for myself, tell me where our channel is here. Yeah, 1 over the slope, right? And what's this axis? VDS. And what's this axis? Well, it turns out, and I'm going to cover this today, that when I plot ID versus VGS and I'm in saturation, if I look at this slope, it's called GM, and it's equal to, it's equal to KP times W over L times VGS minus V threshold N, and it's the same as this. No, it's not 1 over. GM is this because it's transconductance, okay? And it's the same as 1 over the channel resistance, but it's not, they're different things. And I'm going to cover what this means later. So if you don't understand that, that's appropriate. You shouldn't understand what this means, okay? Unless you remember it from electronics. Okay, so let's go ahead and talk, I don't want you to think equations here, okay? I want you to just understand what's happening. So we can talk about the equations, but I don't want you to think in terms of equations because that's not the way you do it in real life. So let's say I have a 5-volt source and then I have a current source, whatever that is, we'll call I, and then I'll connect this to some place, but let's just say I leave it like this for the moment. I know it goes to ground. How do I think of this? What do I think of this as? I think of it, if I have a constant current flowing in a gate drain connected device, so if I write, we'll use the equation, if I write beta sub n over 2 times VGS minus V threshold n squared. If I have a constant current, is there anything in this equation that's going to be non-constant, going to vary? No. So VGS is what? What is VGS here? Constant. Does everybody follow that? So when I see a constant current, we don't know how to generate this, but we will later in the semester. For now, we're just going to use, that's what I used in linear circuits. It's a constant, but I don't know how to actually implement that. Whenever I see a constant current flowing through a gate drain connected device, it provides a constant voltage. Do not think deep here. Constant current through a gate drain connected device, constant gate source voltage. It's a battery. It doesn't change. Does everybody follow? So if I draw another device like this, and I call each of these VGS, I know they're constant. What's the voltage here? No. This pressure plus this. If I'm on the second floor of a building, I went up 1 floor, 2 VGS. I go up 1 floor, it's VGS. I go up another floor, it's VGS. I've gone up 2 VGSs. Just as a sanity check, is the potential here the same as the potential here? Yeah, there's a wire. Is it the same as the potential here? Is the potential here the same as the potential there? No, they're not connected, right? But if I go up here, I can call this 2 VGS as well. Is everybody cool with that? All right. So now, if I ask you, what is the voltage across the current source? Five minus 2 VGS. Whenever somebody asks you what the voltage drop is, you look at one side and you subtract the other side, and that's the voltage drop. Is everybody cool with that? Anybody not follow that? Any questions? Okay, so if I come over here and I connect this device here, this is where I see if I did a good job teaching. And I take and I put a voltage here, we're going to call it Vx. But how is Vx related to the VDS here? It is VDS, right? Does everybody see that? This is equal to, how do I know that? Yeah, that voltage is the same as that voltage. This ground is the same as this ground. And I'm assuming everybody knows when I'm lazy here. When I draw the ground symbol, they're actually physically connected like this, but I don't want wires running all over, right? Okay. So now, if I tell you to plot the current that flows, ID, as a function of, ID as a function of Vx, what do you tell me? Yeah. VGS is constant, right? And I can calculate that. I can go back to this equation, solve for VGS, which is equal to the square root of 2I over Kp times W over L plus V threshold N. What's beta sub N equal to? I'm doing that on purpose just because it's confusing with all the parameters that mean the same thing. Does everybody follow that? So now I get this VGS. Well, what's going to happen here? Got a constant VGS. I've turned the valve on the house, and now I'm going to increase the pressure on the street. So tell me how to plot the current. What is it? Yeah, it's the same old thing. It's like this. But what is the magnitude? If I want to be precise, what is the magnitude, assuming the same size devices? What is this level here? Well, wait. ID is on this, so this has got to be a current. So what is that current? Yeah, it's I. It's got to be. I got the same VGS, the same size. If I have the same VGS, the same size, it's got to be the same current. This guy is mirroring the current in this one. Everybody follow that. Turn the valve on this one the same as I turn the valve on this one, and when I go into the saturation region, the current's going to be the same. That's called a current mirror. It's used extensively in analog IC design. This guy is mirroring the current in this one. Questions? Does it make sense, or am I in here going womp, 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 womp? Okay, so let's write that circuit again on the next page. So I have the following. Oh, before I forget, everybody remembers next week I'll be traveling, so the videos are up. So where are you turning in your homework? My box in the ECE office, and I'm going to ask the grader to pick it up during lab on Wednesday. So you don't come to school on Tuesday, but you come to school on Wednesday, you don't need to make a special trip as long as you get it in there by 10 o'clock. Okay? Because he's not going to, I've already specifically told him not to pick it up before 10 o'clock on Wednesday. I'll tell him again this evening when I send him the grade sheet. He's going to do the grading of the next homework instead of me. Okay. All right, so I got a VGS here. So I can write the VGS is equal to the square root of 2I divided by beta sub N plus V threshold N. How did I get that equation? I just solved this one. And what does it assume? Saturation, which is VDS greater than or equal to VGS minus V threshold N. VGS greater than or equal, greater than what? V threshold. Okay, but wait a sec. How do I know this device is in triode? I'm about to show you something that you're going to use the rest of the semester. How do I know this guy's in triode and not saturation? Well, let me ask a simpler question. How do I know VGS is greater than the threshold voltage here? Yeah, how do I know it's in saturation and not triode? No, okay, first let's ask a simpler question. How do I know VGS is greater than the threshold voltage? And don't think math. Just tell me what's going on. It's got a current flowing through it. VGS has to be greater than the threshold voltage. It's like saying, how do I know the valve is on if there's water coming out of the valve? Right? Okay, next question. What is the drain voltage in relation to the gate voltage? They're the same, right? Does everybody see that? So I'm going to go rewrite this equation up here as VD minus VS greater than or equal to VG minus VS minus V threshold N. Does everybody agree that this equation can be written like this, where VGS is VG minus VS? Okay, so would everybody be cool if I wrote this as VD greater than VG minus V threshold N? But what do I know? Yeah, VG and VD are equal. So is 0 greater than or equal to minus V threshold N? Yes, so whenever I see a gate drain connected transistor and currents flowing through it, I know it's got to be in saturation, operating in saturation. You're going to use that the rest of the semester, all right? So when you see gate drain connected and a current flowing, you think saturation. Questions? So let's go back one more time to this circuit. This was 4. So here, I got my current flowing. I got my 2 gate drain connected devices. They're going over, I'm going to connect them up like this, which is, I believe, what you had in example or in problem 9.7. What is the, in terms, if we call this VGS and this VGS and assume the same size devices, what is that voltage? What's the voltage drop there? 5 minus 2 VGS. What's the voltage at that point? Well, because I'm using this symbol for 5, this is 5. Everybody cool with that? What's the potential right here? Yeah, it's physically tied with a wire over to this. So if this is VGS and this is 2 VGS, by symmetry, what does this voltage here have to be? And what does this voltage here have to be? Okay, so wait, let me pause for a second. What's the current flowing in here? It's turned on the same amount as this. What is the current flowing in here? I. Does everybody follow? They're turned on the same amount. Well, what's the current flowing in here and why? I. Where else is it going to flow? It flows from the drain to the source, to the drain to the source. The current here is to be I, the current here is I. So what does the voltage here have to be? VGS. How do I know that? That's the amount I turn the valve on to get the current to flow. So then I ask, all right, well, what's this potential here? I got 2 VGS here and a VGS drop here. Second floor, then I go down 1 floor. What's the voltage there? VGS, 1 floor. Does everybody see that? So I'm going to do it one more time. Sketch the schematic, and you're going to tell me what happens. And I want you to think in terms of water pressure here. Whoops. Let's just go straight up. And so, just to be complete, what's the current flowing in there? I. Any questions? Yeah, because it's mirroring. If you gate drain connect it, then this current will split and go down this drain, right? It'll flow in the wire and go back down. You don't want that. You want this pressure to be set by this one, this voltage to be set by this one. Okay, so what's the current flowing in there again? I. And what was this voltage? And the current flowing down there is I. So the current flowing in here is I. So now I'm going to put a pipe here. And I'm going to take a current here. We'll call I1, and I'm going to sweep I1 from 0 to I. Okay, when it's at 0, the current that flows through here is equal to the current that flows through here. But as I start to increase that current, that's got to flow in this device, right? But this device can only sink or take how much current? I. So let's put some numbers in. So say this was 10 microamps, 10 microamps, 10 microamps. Let's say I put I as 1 microamp. What has to happen? I'm pushing the water in here 1 microamp. It can't flow backwards through here. Flows down the drain. This stays at 10. Why does it stay at 10? Stays at 10 because the VGS is right there. That's what the valve is set at. So what happens to the current in this one? It goes to 9. If it goes to 9, how is that possible? If I push water in here, what happens to the pressure right here? Wait, if I push water into something, what happens to the pressure? If I push on the door, what happens to the pressure on the door? Goes up. So this voltage goes up. Is this voltage changing? No, it's set over here at 2 VGS. If I put the pressure up here, what happens to the VGS here? It goes down. This one stays at 2 VGS, and this one starts to go up, 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 up. When I get to 10 microamps, how much current's flowing in this device? If all the 10 flows down like this goes up and shuts this guy off. Does everybody follow that? Yes. Yeah, let's just throw some, yeah, yep, yep, let's, well, it doesn't have to be 2 VGS, it could be 2 VGS minus a threshold, whatever shuts the device off. So let's do it with numbers. I like numbers because variables are, I always feel better when I see real numbers. So let's put in, let's put in 20 microamps. Let's use the same size as we'll use in the 1 micron process. And let's put this as 10 by 2. 10 by 2. Then let's go over here. 10 by 2. 10 by 2. And let's say 5 volts. 5 volts. Plus minus 1.2. Or wait, let's say plus minus 1.05. Plus minus 1.05. These are straight out of the book. We'll calculate these later in example 9.5. Okay, and then what's the current that flows through here and why? 20 micro. Why? Yeah, the current mirror. Is everybody cool with that? Okay, so now I come over here. Oh, let's ask one more question. What is this voltage here? And what is this voltage here? Looking good? What is this voltage here? 2.1 minus 1.05 or 1.05. It's got to be, it's a symmetrical circuit, so since I'm turning these on the same amount and I get the same current, the voltages will be, even though they're not physically tied, they'll be the same. Okay? Then I'm going to come over here and I'm going to take And I'm going to sweep the current here that flows from 0 to 20 microamps. I'm pushing water into the pipe there. So as I go to 1 microamp, what happens? What does this do? Still is 20. But what does this one do? It starts going down, because now when I push the water in, pushes the pressure up here. So this might go to, say, 1.01. Well, this stays at 2.1. I'm sorry, 1. How about 1.1? Went the wrong way. I was getting ahead of myself. So this is pressure goes up. Now 2.1 minus 1.1 is only 1 volt. That causes this to shut off a little and the current to drop to 19. Does everybody follow that? And if I go to 10 microamps, well, this still stays 20. This one goes to 10. And this pressure goes up to, say, 0.9, oops, I'm getting ahead of myself again, 1.2 volts. So then the 2.1 minus the 1.2 is 0.9 and shuts us off even further. No, because in the PMOS, the control is up here. Yeah, then it goes, yeah. Yep. So as you go to 20 microamps, this pressure goes up, shuts this guy off. We could do a sim, but I don't want to spend the time today. And all the current comes from here. Now, if you go to 30 microamps, this only wants to go to 20, and so the pressure here just shoots through the roof because it can't handle the 10. It's like your drain getting backed up. Okay, bad things happen. Question? You would have to calculate it. So what you would do is you would say, oh, there's only 10 microamps flowing in this, so let me calculate the VGS. 10 micro is equal to Kp sub n times W over L divided by 2 times whatever that VGS is, minus 0.8 for this process, the threshold, and then you solve for the VGS. Now here's the thing. If I ask you what's the voltage here, and let's say you solve for VGS is 1 volt. Okay? That's VGS. That's not the voltage here. The voltage here would be 2.1 minus the 1 volt, or 1.1. And that's where students will make mistakes, is they'll calculate the VGS and go, I'm done! And then they won't do the subtraction and get the actual voltage. Yeah, that finds this VGS when it's only got 10 micro. And then subtracting it from the 2.1 gives me the voltage there. Yeah, so VS is going up and it makes sense. If I put more and more pressure here, this is going to shut this off until it goes all the way up. All right, any questions on that? You intuitively understand this kind of circuit? We're going to see this again later in the course. Yes. Yep. Yep, these stay constant. Yeah, always. Because no current flows into the gate, so whatever I put over here as far as MOSFETs, that's not in my mind. I can get a really complicated schematic. This stuff over here doesn't pull any current, so when I'm calculating the voltages, I ignore this stuff. Then once I've got these voltages, then I can see where they go. And it turns out, if you calculate, if this was a 20 by 2 device, all you do is you take whatever current that's flowing in here, 20 micro, and if you look at the equation, this becomes 40. And that's how you adjust the currents. And actually, this is how you make it. If I were to represent this side of the transistor, this point right here would be a current source like this. And that's how integrated circuits actually make a current sink. And I use PMOS for a current source. We'll talk about that in chapter 20. This one? Nope, never change. All right, one more question? Okay, let's talk about transconductance and the small signal model for transconductance. And let's see, that is slide 6. Okay, so, and let's use brown. So what I'm going to do here is the following. This is probably, of all the small signal parameters we derive, this is probably going to be the most important because we'll use it over and over again. But you have to understand how it works. So here I've got my transistor, and let's switch this up. I got my VGS here. I got my AC VGS. And I'm going to do a sim with this one so that you can verify that what we're doing is right. And let's just say it's 10 by 2. Let's say VGS is 1.05 volts, and little VGS is 1 millivolt. And then I'm going to come over here and I'm going to put a DC voltage here of, how about 2 volts. Okay, is it in saturation? Is VGS greater than the threshold voltage? VGS is 1.05. Threshold voltage is 0.8. Is VGS greater than the threshold voltage? Okay, is VDS greater than or equal to VGS minus V threshold N? Yeah, drains 2 volts, gates 1.2 volts, so yes. Does everybody follow? Now, this current here is going to have a DC component and an AC component, just like we did with the triode. Does everybody follow? Let's just focus on the DC component to begin with, and here's where I cringe and hope everybody studied their quiz. If I plot ID, the DC component, versus VGS, what do I get? Yeah, it just goes up, right? Like this. This is the case where I'm standing in my yard and turning on the valve and plotting the water that comes out, and after I hit the threshold voltage, water starts coming out after I turn it past a certain point. Okay? Anybody not understand this? Because I don't want you to go through the class and say, that was magic. Okay? Everybody follows this. Yes? Flattening out. Yeah, if you keep turning this up more and more and more and more, this is no longer valid, and then it'll roll off and flatten out. Yeah, but we generally don't talk about that because we don't want to operate in that region. It's like if you're designing a valve for your house, you generally don't want to talk about the situation where you've turned the valve on so high and the pipe so big that the water company can't supply water to your house, right? Okay, you want to assume the water company's got enough water for you, right? Which I hope that's never a concern in my life. All right. So what I'm going to do now is I'm going to wiggle the VGS back. So I'm going to bias up here, and I'm going to wiggle back and forth on that curve. That amount of wiggle, I'm going to come down here. I'm going to say that is VGS. So I'm in the yard. I've turned the valve on. I've got some water flowing, say 2 gallons per minute. And then I turn the valve back and forth, and I wiggle it back and forth, and I ask, how much does the water change? Now, think about it for a second. If I can turn the valve just a teeny amount and get a significant change in the water, meaning this curve is really steep, then I'm going to have a large transconductance. So if I just turn it a little bit, the water changes a drastic amount, that's a large transconductance. Same thing here. If I put a teeny little AC VGS in and I get a large variation, that means I have a large transconductance. I say transconductance, and that's the slope here. It's GM, and it's the rise over the run. The amount of AC current that flows for that wiggle is ID. That's the rise, and the run is VGS. And so this is the equation that everybody always forgets, but we'll use it hundreds of times in this class. I'm going to derive it, but notice I'm assuming that the DC VGS is is large compared to the AC. In other words, I'm assuming that I've turned the valve on enough that when I wiggle it, I'm not wiggling it enough to shut it off. I'm wiggling it so that it's small compared to the amount it's on. Everybody follow that. So if I want to determine the GM here, transconductance, what do I do here? Same thing we did with the channel resistance. Take the derivative with constant VGS and constant DC ID. So I'm going to rewrite that equation as ID plus little id is equal to Kp sub n over 2 times W over L times VGS plus little VGS minus V threshold n squared. That's the equation describing this in the saturation. I can rewrite these two variables as, lowercase meaning AC, but uppercase subscript meaning DC plus AC. I can rewrite this as, does everybody follow? So when I take the derivative, GM is equal to the derivative of ID with respect to VGS at ID equal constant and VGS equal constant. In other words, at this point, when I take that derivative, this comes down, cancels with the 2, and gives me Kp sub n times W over L times VGS and times the derivative. What's the derivative of VGS of the stuff in here with respect to VGS? 1, right? The derivative of x minus a constant with respect to x is 1, dx dx. Anybody not follow that? I'm having nightmares you didn't learn calculus. If you say it's been a long time, we'll compare notes. Okay. Whoops. Let's write it out. Let's write VGS minus V threshold n. Is everybody cool with that? But if we make the small signal approximation that VGS is much, much larger than VGS here, we can write that GM is equal to Kp sub n times W over L times VGS minus V threshold n. When you took electronics, did you get what small signal approximation was? Cassandra, did you? Okay. She took it from me. That's why I'm asking. She was like, no. All right, what else are you going to say? All right. I'm going to do an example now, and we're going to sim and make sure we understand what's going on. I'm going to do 2 different kinds, but this is super important for the rest of the semester. Does everybody understand what we're doing here? No, saturation. So I've got, remember, saturation is when I turn the valve on and the valve on my house is limiting how much water is coming out, not the street. And then all I'm doing is I'm wiggling the valve back and forth to get a change in the water that comes out. So I wiggle it, say, 1/8 of a turn, and I get a change in the water. Say it changes from 1 gallon per minute to 1.1 gallon per minute. And then I'm going to say that, oh, 0.1 gallon, that change divided by 1/8 of a turn, that's my transconductance in water per turns. And here it's in amps per volt, which is, 1 over resistance, right? Okay, so let's do an example. What's that? Well, it's just the transconductance. It's the ratio of the change in current with voltage. Just like resistance is the ratio of voltage with current. Okay. So here we'll do our example. I'm going to do it step by step because we're going to use this over and over again. Remind me though, what is the Kp for this 1 micron process? And that's 1 over ohms too. That's the same units as transconductance. And what's the threshold voltage? Okay, so let's do the following. I think I used 2 volts, that's fine. So let's calculate ID. Tell me how to do it. 120 micro divided by 2. This is a 10 by 2 times 10 by 2. What do I use? Okay, so does anybody bother that I use 1.05 instead of 1.05 and the AC plus or minus 1 millivolt? No, that's the whole point. Whenever you do small signal AC analysis, you do the DC calculations first, because all of small signal AC parameters are based upon DC biasing, where I've set the devices, the VGS and the ID. Okay, that's the same way SPICE does it, and we're going to do this in a moment. Okay, so if I calculate this, I get, let me do it in my head, 0.25 squared times 5 times 120/60, 20 microamps. Okay, let's verify that with simulation. That's why I picked this. When I did the book, when I wrote the book, I picked 20 microamps and I calculated what the VGS would be. And for the nanometer process, I picked 10 just to be different. And we'll see how we pick those later and what's the considerations. So let's go back to our little SPICE file here. And let's pick, what the heck, how come the icons aren't showing up here? Oh, there we go. All right, let's just pick one. Let's pick, how about this one? Let's see where we're at. Oh, this is a PMOS. Let's pick, okay, that's random. So we'll hit File, Save As. This is Lecture 4, Example 1. See, if I did PowerPoint lectures, I could just point to these and say, in this one I did a sim. Wouldn't that be awesome? Yeah. Okay. So let's, I just want to show, I'm doing my homework here. I just want to show that I calculated the DC correct. Tell me what's the best sim to do that. Yeah, let's just do a .op. All right. I could do a .tran too. Let's do both. Let's live it up. Okay, so let's go to .op. Boom. Then let's change the size of the devices to 2 and 10. And let me just pause for a moment. Got my include so it doesn't use the wrong models and give me the wrong results. I got to do one other thing. 1.05. Hit save. What do I care about? What am I going to be looking at here? Do I need to look at this voltage in the sim? No, because I know it's 1.05. Do I need to look at this voltage? No, I know it's 2, and these two are ground. The only thing that I don't know is what the current is. And I can pull it up, and it says ID is, oh, I'm off a little bit, 17.2 micro. Now I'm going to show you something real quick. See how it's 17.2 micro? 17.24 micro. You can go here and then look at the bottom, and it shows it as well. Watch what happens if I increase this to 5. And I rerun. Now it goes up a little bit. Does everybody see that? Okay, so I expect that. So let me put this back at 2. And before I move on, let me basically show you something, because we're going to use these sizes and currents over and over again. If you look in the back of the book, if you look here, and you need to understand this, because if you don't understand and you just say, well, it's in the back of the book, you're not going to do well. This current and this size and this VGS here, 1.05, and this is called the VDS SAT because it's VGS minus the threshold, which is 250 millivolts. These are valid for only these devices. So if I change the device size to 15 by 2, that doesn't make sense. That doesn't make sense, and that doesn't make sense because the current isn't the same. The only time these are valid is for these sizes and currents and VGSs. Does everybody follow? So if I tell you, oh, this device has a size of 10 by 2 and there's 20 microamps flowing in it, then you know the VGS has to be 1.05. Because if you have two things fixed, you can't change the third. If I said, oh, the device size is 20 microns, but the device current's 20 microns, but the device size isn't 10 by 2, then you know the VGS isn't going to be 1.05. Does everybody follow? But these numbers that I calculate here we're going to use over and over, and I don't want you wasting time. I mean, we'll do calculations with different sizes, but I don't want you to recalculate these if they're given. Yes? No. I could increase the size. Yeah, then it can't. Yeah, it can't. Yeah, so you can't go above the 20 if you keep the VGS the same and the size the same. I mean, it'll go up a little bit as I just showed, but there's a phenomena called breakdown that if you push it too hard, it'll break down. Yeah. Okay. Is everybody cool with that DC sim? If it says use the parameters, like in the book, if it says use the parameters from table, that's in one of the tables, 9.1, I think it is. I just put it in the back too, so it was easier to see. Then you don't have to recalculate. No, KPN doesn't change. The process, KP and threshold always stay the same. We can change the W over L, which will change the current and the VGS. Now, if we go use a different process, like we'll talk about the 50 nanometer process, then those will change. Okay, any questions on this? So I'm going to go now and I'm going to write GM. I just derived it. And GM, I'll write the equation, is Kp sub n times W over L times VGS minus V threshold n. And that's equal to 120 microamps per volt times 10 over 2 times, and I'm going to be a little different, 0.25. Is everybody cool with that? And if I calculate that, that's 150 microamps per volt. So I'm going to ask you some questions, and you're going to tell me what's going on. What's the DC voltage here? 1.05. What's the DC voltage there? 2. What's the DC drain current? Close to 20. We got 17.4, so we're off a little bit. Okay? Questions? Okay, now, what's the AC voltage there? 1 millivolt. What's the AC voltage there? How much AC voltage is dropped across that DC? None. What's the AC voltage there? Okay, what is the AC current that flows there? ID. I'm wiggling the valve back and forth. It's GM VGS. In this case, it's 150 microamps per volt times 1 millivolt, which equals 150 nanoamps. The AC voltage. This is the thing. If I ask, what's the water pressure changing on the connection to my house? The water pressure is not changing if I've got a good connection. But can I change the amount of water that flows? Sure. I'm doing that with my valve. The water changes back and forth, but the water pressure stays constant. Does that make sense? Okay. Do you? Well, no. Assuming you got a big water supply to your house, right? And then that pressure is constant, say 60 psi. Then you get in there and you're changing by 1 cup. Well, that 1 cup's a negligible amount, so the pressure doesn't change. I'm holding it. If you don't believe me, I'll show you in the sim. I'm holding the pressure constant, but the amount of water, because the pipe's so big, is still changing. The pressure doesn't change. But let's find out. And if I'm wrong, then you can go, you're wrong. If there's resistance of the wire, there's resistance of the pipe, and that comes into play, yes, then the pressure will change a little bit because you're putting the pressure change water through here and it's dropping across the resistance of the wire. If that's an ideal, million-mile diameter pipe where you never change, where there's never any pressure drop across the pipe, you can change the water flow in there all day long and it won't change the pressure. But let's find out, shall we? Yeah, that's the valve turning on. This is, 1 millivolt changes the amount of charge underneath and modulates the current. It's just moving back and forth on the curve. Okay, so let's do the sim. Let's hit save. I'm going to do the .tran for both DC and AC, but first I'm going to do it AC. And I'm going to do this to make it so you don't get confused. So I'm going to close this, and that was lecture 4. And then I'm going to say File, Save as Example 2. And I'm going to do a small signal analysis, which is an AC sim. And I'm going to simulate from a decade. And what does decade mean, people that were in my lab yesterday? 10, right? Yep. And then let's go 100 points per decade. Just some arbitrary large number. Start frequency 1 hertz, stop frequency 1 kilohertz. Hit OK. If I plot the AC voltage here, what am I going to plot? 0. If I plot the AC voltage here, what am I going to plot? Oh, well, I got to put that in here, don't I? So I got an AC amplitude of 1 millivolt. So does everybody see this is like 2 voltage sources in series, a DC of 1.05 and an AC of 1 millivolt. I'm going to hit save. Now I'm going to hit run. I'm going to plot what is 1 millivolt in dB? Minus 60. So if I got 20 log of 1 millivolt, which is 10 to the minus 3, that's minus 60 dB. But I don't like dB. dB scares me. What is dB an abbreviation for? Decibels? No, dead body. Would you see the dB? All right, so let's go look. There's my 60 dB. Now you're never going to say dB without thinking that. All right, let's go to linear. And there's my 1 millivolt. Everybody cool with that? Okay, how do I plot the current? Go over here. Boom. Oh, I can't see the 2 on the same plot. That bothers me. So I'm going to right click here, go to add plot plane. Then I'm going to drag this up. And there's my, I calculated 150, but it's a little bit less than 150. It's 129, in the ballpark. Any questions? There's some secondary effects that'll change a little bit. That's why I'm not trying to be precise with all this, because there are so many things, and especially in real devices like the 50 nanometer, they're very sensitive because they're so tiny to pressure changes in other places. So before I leave this, let me hit the save. Does everybody see what I did to give good homework so the grader, me, likes what he sees? Okay. So what I'm going to do is I'm going to go over here. I'm going to select this window and I'm going to go View. And here I can see the net list. I'm going to look at the SPICE error log and I don't see anything. So I'm going to go back and do the same thing with the first sim. Actually, let's do this. View, List. Go back to the first sim and do the same thing with the .op. Run. Comes up. Then I'm going to go to View, SPICE error log. Why am I doing this in a .op? Because it tells me how far off I am with my transconductance. It tells me what my DC current is. It tells me, oh, I calculated 150. It's saying 129 microamps per volt. That tells me how far off, so I know where the issues are if I'm not doing it right. Does everybody follow? Okay. Arming you with all this knowledge to solve problems. Okay, so now let's go do the sim again. Any questions? Yes? Oh, remember that there's the sub-threshold current that flows below threshold. So if you go look at the models, and we're not spending time on that because spice modeling of MOSFETs is a big deal. You have all these other parameters that influence the calculated threshold voltage. So there we're saying, hey, the zero bias threshold voltage is this. But we have all these secondary effects that come into play that modify, that try to make the device behave more like it actually is when you fabricate it. Okay. And so you have these things, and remember also, threshold voltage isn't where there's zero current, go from zero current to having some current. If you look at the curve, it's rounded, and you still have a little bit of current flowing in there. And I'll talk about that, I hope, when we talk about the sub-threshold slope. Okay, the key point is there's no magic to go from no current to having a current like there is in a valve. There's always a little leakage, and that's actually a really big deal nowadays, because you got billions of transistors, so they leak a teeny amount. You add them all up, and it's a significant amount of current that drains your battery in your cell phone or whatever. Okay, so let's go do one more sim on this, which is the same thing, except notice, repeating myself, this, oops, this sim is an AC sim. So I'm going to do I want to do a time domain sim, and I want to do show a sine waves. I want to look at things in the time domain so I can see sine waves. Okay, so what I'm going to do is I'm going to do the following. I'm going to do a save as, call this example 3, save, and then I'm going to change this sim to a transient, say stop at 5 milliseconds, start saving the data. Sims always start at 0, but you may not want to look at the beginning of the simulation because it may be garbage like startup or whatever. And then leave it at that. And then I'm going to hit the run button here. And I'm going to then plot this gate voltage, and I see 1.05. Well, wait, where's my 1 millivolt sine wave? Nope. This AC has nothing to do with a transient sim. Just like if I change this to a sine wave, the sine wave has nothing to do with an AC sim. You don't know that, you're going to get frustrated. AC is for AC, sine is for transient. Sine is not for AC. Okay, so I'm going to put my sine wave in. My offset is 1.05. That's my DC bias. My amplitude is 1 millivolt. And let's put a frequency of 1 kilohertz in and hit OK. So now it says AC of 1 millivolt, but I got a sine wave here. That's 1.05. Notice that if I go do an AC sim now, I got to check to make sure that the DC still shows up. Okay, so let's hit run. Ooh, what just happened there? Okay. In LT Spice, it was designed to model switching mode power supplies. And so they throw data out in order to keep the raw data files small. And there's this question's answered on the CMOS EDU website. I don't want to spend time on it. You'll see it here, and you'll have it in the examples. You have to do dot options in order to get rid of that compression, so it throws the data, doesn't try to compress the file. You put dot options, plot when size equals 0. So I do that, and it won't use compression now in the data. So when I hit run, boom, there it is. Okay. Yeah. Is everybody cool with that? Does everybody see how I've got the 1.05 and the 1 millivolt? Any questions? Well, I got a question. I want to see the current flowing. So I'm going to go add plot plane. Then I'm going to probe here. And what do I expect the current to look like? Tell me before I do anything. What is it? Yeah, the AC plus DC. So 17.4 micro, and writing on that's going to be a sine wave. Now, let's go ahead and plot that. There it is. Does everybody follow? No magic, right? Everybody follows what's happening. Now, here's an issue. When I go plot and I do my homework, if you put something, let's say this is what you got, and you can look at the magnitude, it's going to be 129 or whatever it is. You can subtract out here. Let's do that. Let's say minus 17.22 micro. Let's see how far off I am. Okay, so see, I've got it swinging nearly around 0. That needs to shift down a little bit more. Does everybody follow how I've subtracted out by right-clicking on the trace? And actually, let's not do that. Hit OK. Hit save on that plot. Does everybody understand? Now, if I have another circuit, let's say there's another current I want to plot and I want to look at the AC, but its DC bias is slightly different. Say it's 15 microamps. If I go up here and I say add trace and I write 15 microamps just to add a DC, and I plotted, oops, what did I do? Put 15 micro, I want a 15 microamps. And I put it there. Does everybody see how if they're significantly different after a while, let's say I put this at 1 micro. I won't be able to see the AC. They'll both look basically constant. Does everybody follow that? So I have to add a plot plane or I have to subtract the DC from the signal. Any questions? What's that? Yeah, because if I've only got 0.1 micro and I'm displaying 20 micro, it's going to be a small amount when I put things together, right? Does everybody follow that? Okay. The what? This thing? There is no point. I can get rid of it, not show it, hit run, and it's the exact same thing because it's ignored. But now, if I want to go back, let's close this, save this, and then let's close that. Notice when I close it and then I reopen it because mine set up so that every time I close it, it deletes the raw file. And I don't want to post the raw files on the page, so it's not that I'm wasting time. So there I go here and I say, oh, I want to now save as. And I go to example 4. And then I go, let's make an AC sim again. 100, decade, 1. I'm just picking these frequencies arbitrarily. Okay. And I go, okay. What's my AC and what's my DC here? My AC is 1 milli. And we have to check to make sure that it uses the DC offset of the sine wave. So let's go hit run. And we hit the curve here, and it says, hey, the DC operating is 1.05, and that's set by the DC offset of the sine wave. Okay, if I plot this, there's my minus 60 dB, which is 1 millivolt, and it's not showing up because I right-clicked on here and said, don't show this or make this visible. Does everybody follow that? Any questions? I want to cover one more thing real quick, and then we'll do our quiz. Yes? Okay, for small signal, I can sweep the frequency and look at what the response looks like. So I could say, hey, at 1 kilohertz, the gain is 5, and at 10 kilohertz, it's 1. If I do transient, small signal assumes signals are small. So if I put in bigger signals, then I'm not going to see any distortion, it moving down the curve and running. Like if I'm doing an audio amp, which is what the project was last time, if I have bigger signals and I do a small signal, it's just going to say perfect behavior. So I have to use a transient to look at the behavior for distortion in larger signals. All right, let's cover one more thing real quick. And that is, I'm going to mention it, and I'll probably, in the videos that you watch next week, because we don't have class, and you're turning in the homework that's due on Tuesday or by Wednesday before 10 o'clock in my box. So don't go to the ECE office at the last second, because if they're out at a meeting or whatever, you won't get in. Of course, if you do that, you can always walk over and hand it to Jan in TBE350 because he'll be doing the lab. The last one I want to really discuss, a small signal model, and I'm just going to tell you the result, and you can look at I may cover it in the book, is this one. For the MOSFET, as you increase the VDS, you get this curve, and then what's the slope of this curve? It's 1 over R out, which if you do the derivation is lambda ID. Lambda is the parameter to measure the slope. And so you can write R out is equal to 1 over lambda ID. So in the saturation region, we're going to model the device. The small signal model is going to be GM VGS. There's my ID. What are these two terminals labeled as? Drain and source. That's the current that flows. Here's my gate. What do I label this voltage? Yeah, VGS. Okay. I'm going to add a resistance here to model this slope, and this should make sense to you, of R out. And R out is 1 over lambda ID, and you can look at the online or for the video or just read the book and see how that's derived, or you can ask me when I come back if you don't get it. But it's the same old thing. Bias here, apply a voltage between the drain and source AC, look at the current that flows, the ratio is R out. Any last second questions? Any last second answers? Answers are better than questions.